Hello students, I hope before watching this video, you people might have watched a video on root locus construction and also Bode plot construction to comment on stability of any control system. I hope you have understood root locus and Bode plot. Now in this video, we are going to learn how to plot a frequency response based on Nyquist criteria. Okay, so this is Nyquist criterion. So Nyquist is the name of a person who gave this particular method, in commenting stability of a control system. So this is very, good method. The reason for Nyquist criteria, the benefit of Nyquist criteria is Nyquist criteria comments on stability on both conditions. So it comments on stability whether open loop. So when a control system is under open loop, stability is also possible to comment on stability for an open loop control system. Nyquist will also comment on closed loop control system stability. So Nyquist comments on both system stability. It comments on open loop stability, means what is the stability of an open loop control system. It also comments on stability for a closed loop control system. So this is what Nyquist criteria says. Okay, let me come to the Nyquist contour. So we have two diagrams here which you can see here. We normally call this as Nyquist contour. So here, these are the two diagrams, and each one of these diagrams are being used as a basic or a base graph that we keep in mind while plotting the Nyquist plot for any given question that we are going to solve. Okay, so we are keeping these two diagrams as a basic base diagram. Now, when do we use this as a foundation diagram, and when do we use this second diagram? So let me tell you. So the first diagram, let me label it as A, and let me label this as B. Instead, I'm not explaining you like how we got these two diagrams, but anyway, let me tell you, these two diagrams are nothing but an explained diagram. So both are explained diagram where a Nyquist contour is written. Both are actually explained diagram. Okay, so you have written a Nyquist contour. This semicircle, if you see here, this is a Nyquist contour written for condition A, and this is a Nyquist contour written for condition B, and both the contours are written in the right half of S plane. Keep that in mind. Whatever we see this side is actually right half of S plane. So we have written this contour, Nyquist contour, in the right half of S plane. Even here also we have written the contour in right half of S plane. But when do we use this contour and when do we use this Nyquist contour? That is the very important factor which you people should know. Okay, before knowing that, let me explain you what are the different things that we need to keep in mind. Now, as we all know that in any S-plane, we have horizontal, which is a real axis where you see all real values, whereas vertical is all, imaginary axis where you see all imaginary values. If you see here, I have labeled each and every point with an alphabet. So A is a point at the origin. Okay, A is at the point at the origin, whereas B is the point at infinite omega. See, J plus J infinity means omega is infinity. Okay, this omega is infinity. Okay, so an angle, if you see at B, it is nothing but 90 degrees. If you see here, right? Similarly, we have a point C, and that point C is a semicircle where the radius of that semicircle is tending towards infinity, because the real value can change till infinite plus infinity. So therefore, the radius can extend till infinite. Okay. Normally in the problem we consider this r into e power j theta. I'll tell you where we will consider this parameter. And this angle, I'm sorry, not the angle is, this is angle is what do you say? This is not the angle. I'm sorry. The angle is, this is the angle theta. Okay, this is the angle theta. When you come to D, point D, you can see here the point D is at minus infinity. Omega equals, so this is the point where omega equals minus infinity. Okay, and the angle at D is minus 90 degree. Fine. So if you go towards right half of S plane, the angle in this horizontal line is actually plus 180 or minus 180. Okay. Now coming to this particular contour, you are able to see two semicircles. One is the small semicircle, if you see here, this is a small contour, what you see here, and you also have a upper, bigger one, which is a bigger contour. Now, as we have two semicircles, this semicircle will try to approach towards zero. Why towards zero? Because this is 0 point. It is very near to origin. That is the reason I have taken small r tending towards zero. Whereas this green line, what you see, is tending towards infinity, because this is the contour which is written on a real axis where this can approach till infinity. Okay. So therefore, this varies with r into e power j theta if an angle theta is considered here. This is theta. Whereas this contour is r into e power j pi. Okay. E power j pi. Fine. Now, where do we use these two contours? Are we using both the contours as a foundation, Nyquist contour for plotting the Nyquist plot for any given problem? That is what we need to know. Okay. Now, this contour will be considered when we don't have any pole or zero at the origin. Keep that in mind. When we don't have any zero or pole at the origin. It means that you need to have an equation where k divided by s plus a format. It means that we don't have any s term here. See, s into s plus a means there is one pole at the origin. So we don't have that term. Okay, we don't have s in this particular condition. Even if I have k into s, for example, even that s is actually 0, which is at the origin. So we don't have that also. So therefore, in such conditions or in such case, we are going to consider this contour. Okay, this is the contour which we consider when we don't have any pole or zero at the origin. Now, this contour, what you see, is considered as a foundation contour in any problem when we have any one pole, or means when we have any poles or zeros at the origin. Keep that in mind. So this will be considered. This contour will be considered as a foundation contour when we have any zero or pole at the origin. At the origin. So we will consider this contour when we have any zero pole at the origin. The reason is, let me tell you very simple. If I have a pole, for example, if I have a pole at the origin, and you know that it becomes s into s plus a. Now, if s is equal to 0, for example, now anything divided by 0, see k by 0, that becomes infinite. So therefore, when there is any pole at the origin, I cannot traverse the contour, I cannot traverse the transfer function through 0. That is why we have taken a semicircle, small semicircle, which is outside 0, outside origin. Understood? The only reason, because when s equals 0, the transfer function becomes infinite. The transfer function becomes infinite. So once the transfer function becomes infinite, there is no meaning at all. So that is the reason, because we know that s equals 0 at the origin. So when s equals 0, that you substitute in this equation, this entire equation becomes infinite. So that would be the reason why we take this small semicircle, which is outside the origin. I hope you all understood what I am saying. Whereas in this case, if s equals 0, you don't get any sort of infinite transfer function here. Means you don't get g of s into h of s, which is open loop transfer function. That doesn't become infinite in this particular case. And that is the reason we can traverse the transfer function through origin. Okay, so through origin we can traverse. Understood? So this is the reason why we take this contour as a foundation when we have an equation which is given for us in the question which doesn't have any pole or zero at the origin, whereas this contour is considered in solving the problem when any transfer function is given with pole or zero at the origin. Okay, I hope you understood what I am saying. Now we'll see what are the steps involved in solving the given question for commenting on stability using Nyquist criteria. Okay. So let us see the steps involved in drawing the Nyquist plot to comment on stability. Okay, step by step we are going to write now. So the first step is we need to generate the transfer function for the open loop. Anyway, if it is not given, we need to generate, or Normally the question they will directly give you the transfer function. So that is g of s into s of s equals, that will be normally in the form k into s into s over z into s plus a into s plus b on divided by s power p into s plus x s plus y. So this is the transfer function that you will have, or it will be given in the question. So what is this actually is, k is already, we know that it is a gain, whereas if you see what is s power z and s power c, so these are the, poles at the origin or zeros at the origin. Whereas if you see these two terms, s plus a and s plus b, so these both are zeros, simple zeros, and this s plus x, plus s plus y, if you see, these are simple poles. Okay. Anyway, this transfer function will be given to you in the problem. Okay. Now the second step is we need to check the transfer function has polar zero at the origin. Polar zero at the origin. Now, if you have polar zero at the origin, we are going to take this contour. Normally, pole at the origin, because zero, when we put zero, s equals, in the numerator, and if you take s equals zero in the numerator, the entire transfer function becomes zero. But when we have s equals 0 at the denominator, then we have that transfer function which becomes infinity. So this contour is considered normally when we have pole at the origin. So when we have pole at the origin, this contour is considered, or when we have no pole at the origin, then this contour is considered. So we need to write that contour. So we need to check first the transfer function as pole or 0 at the origin and write the basic contour diagram. Write the basic, contour diagram. Write the basic contour diagram. Okay, so this is the basic contour diagram. This is basic contour diagram. Out of these two, you have to write any one based on the contour. Coming to the third step, we need to identify, or we need to find out. The number of poles. We need to find out the number of poles. Lying in the right half of this plane. In the right half of S plane. So we need to identify, or we need to find out the number of poles lying in the right half of the S plane by writing pole zero diagram. By writing pole zero diagram. Pole zero diagram. And this number of poles which is lying in the right half of S plane, this number of poles which is lying in the right half of S plane is denoted with the alphabet P. This is very, very important parameter that we find out, which is P. Now, if P, capital P is 0, means if you don't have any poles at the right half of S plane, then we say the system is stable, but here we say open loop system is stable. When P is 0, then we comment saying open loop system is stable. It's stable. If P is not equal to 0, then we say closed loop system is stable. Then we say closed loop system, if P is not equal to 0, then we say open loop system is not stable. It's not stable. Okay. So that is what you need to keep in mind. You need to calculate the value of P. And if P is 0, then we comment saying open loop system is stable. And if P is not equal to 0, we comment saying open loop system is not stable. This is the third step which we calculate P. Now the fourth step what we do here is, we try to perform the conformal mapping, or we also say find the image of the contour A B C D A, or A B C D E F and A. So we have two types of contours. So this A B C D A will come when there is no pole at origin. Okay, you are either doing ABCDA or ABCDEFA will come when you have pole at origin. It means that if your basic foundation diagram is written, if the basic diagram written is this, then you are going to draw the conformal mapping for A, B, C, D, A. And if you are having the basic foundation diagram is this, then you are going to try to find out the contour A, B, C, D, E, F. So you are going to also traverse with this small semicircle. That is what I am saying. Okay, so that is what we do. Then the next step what we do is the fifth step. The fifth step is after finding the contour ABCD A or ABCD EF A. The fifth step what we do is we are going to find the encirclement. We are going to find the encirclements, and this encirclement is denoted with the alphabet N. So I'll tell you, once we write this conformal mapping, which is the contour for ABCDA or ABCDEFA, we are going to find the number of encirclements, and that encirclement is denoted with alphabet N. Now, if the encirclement is clockwise, then if the encirclement is clockwise, then the capital N what you have here is considered to be, positive, and positive. Now if the encirclement is anti-clockwise, then the encirclement value is negative. And the value of N depends on the number of encirclements. The value of N depends on the number of encirclements. You can have one encirclement, so N becomes 1, and you can have two encirclements where N becomes 2, and if both encirclements are clockwise, then it is plus 2. If both encirclements are anti-clockwise, then it becomes minus 2. Okay? Now, once all these things are identified, then we are going to have the sixth step, which is finding the value of Z, where the formula for Z is P plus N. So this is very, very important. This is the final thing we do in Nyquist. So Z equals P plus N. If Z equals 0, then closed loop system is stable. So Z depends on commenting whether closed loop system is stable or not. So when Z is equal to 0, the closed loop system is considered to be stable. It's stable. So when Z is not equal to 0, then unstable. Closed loop system is unstable. So what Nyquist says is, okay, initially the system is open loop and you found the value of capital P and you found it is 0 or not 0, where you comment saying open loop system is stable or unstable. Now, when you convert this open loop system into a closed loop system, we need to check whether closed loop system is also stable or not. Okay, so that is very important. See, you use a lot of devices at home like fridge, washing machine or anything, which is all considered to be an example of control system. Some devices need to be an open loop so that the stability is good. If you make it closed loop, then it becomes very expensive, and meanwhile the complexity of designing such system will also become very difficult, and stability might also be reduced if you add a feedback into that. And some of the devices, we need that to be closed loop, so we cannot keep it as open loop. So therefore, we need to check what is the stability when it is converted into a closed loop. Okay, so therefore, Nyquist comments on both closed loop and open loop stability. Okay, so capital P predicts on closed loop, open loop, whereas Z predicts on closed loop. Now, think the open loop is P equals 1. So it means that there is one pole at the right half of S plane. So this, when P equals 1, it says the open loop is unstable, right? When P equals 1, it says the open loop is unstable. But when Z equals, think you got an encirclement which is anti-clockwise. You got one encirclement which is anti-clockwise, so that N will be equal to anti-clockwise is negative and one encirclement which says N equals -1. So what happens to ZL is you have P1 whereas N is -1, so this makes Z is equal to 0. So, though the system, when it is open loop, it is unstable, but when it becomes closed loop, it is stable because Z equals 0. So, this is what Nyquist says. So, you cannot keep a system which gives you stable when it is closed loop. So, such system cannot be considered to be an open loop. Means you cannot keep such system under open loop condition. You have to consider that system as closed loop only. Because when it is open loop, it becomes unstable, whereas when it is closed loop, it is stable. Okay. So, this is the steps involved in finding the stability based on Nyquist criteria. And how to find the encirclement and how to perform the conformal mapping. These two steps I will be explaining you in the problem itself in the next video. Okay, I hope in this video you understood what is the basic fundamental foundation that you need for understanding how to plot a Nyquist criteria and to comment on stability. Okay, so we'll try to discuss further much details when we solve the problem in the next video. Thank you.